Thank you very much. So I'm gonna share my slides. I guess it's easier. Can you hear me well?
We hear you perfectly. We still don't see your slides. So.
Okay, I'm gonna bring them up.
Yes, now we see the slides. Yeah.
Perfect.
Please go ahead.
So, hi everyone. So first of all, thank you very much for the organizer of this conference for inviting me to speak today. So my name is Mathieu Ducroux. I'm a researcher at N-Chain, which is an R&D company specialized in blockchain. And we're based in Switzerland. So I'm talking right now from Switzerland. So one topic that I'm particularly enthusiastic about is studying how blockchain technology and its unique properties can be used to enhance the security of the internet. So this is what I'm going to talk about today. So recently, with what we call Web3 and all the Web3 related projects, we've seen this movement advocating for a more secure, private, and ultimately decentralized internet. So what I would like to show you is how, from a technical point of view, we can leverage blockchain technology, which is the main technology behind Web3, to enhance the security of the internet. So in the first part of this talk, I'm going to go over some examples of internet protocols that can be enhanced using blockchain. So I recall this morning, there has been a number of speakers talking already about that, about DNS, about IoT, about CGA. So I will complement that in this talk. And then in the second part, I'm going to present some more recent research that I've been doing around the secure generation of IPv6 addresses using the proof of work computed by Bitcoin. So the first protocol we'll be looking at is BGP, which is a routing protocol standardized by the IETF, which is used by routers to announce and find routes packets should take around the internet, and in particular across ASs, which are these big networks managed by a single entity. So BGP is basically based on a weak trust model where ASs assume that the neighboring ASs will propagate the correct route information. And in practice, we've seen many examples of malicious ASs broadcasting false information to hijack the traffic sent by the routers. And so there have been a number of proposals to use blockchain to enhance the trust on this BGP announcement. So the first one is Route Chain, which is essentially a blockchain that is run by ASs, where ASs can agree through consensus on the correct BGP information. And this makes it harder for an attacker to propagate malicious BGP announcement. The second one is BGP Coin, which is an Ethereum smart contract that can be used by ASs and IANA to manage the internet number resources. And so both of these projects are using the transparent and tamper-resistant property of blockchains to enhance the trust among ASs. Now, I should also mention that there has been worked at the IETF level to review opportunities to use blockchain to secure BGP. And this has led to the creation of an internet draft that you can find here. Okay, so then the second area in which blockchain can help is PKI. So there's already been a lot of research on that. So I'm just going to summarize the three main aspects in which blockchain can help. The first one is in the validation of certificates. So the idea here is to have certificate authorities issuing the certificates directly on chain. And these certificates can be validated automatically using smart contracts. And so for users, what this means is that checking the validity of a certificate is as simple as checking that the certificate was put on chain. Now, related to that, we can also have, using blockchain, much more efficient revocation of certificates. So we can use the blockchain as a single source of truth that anyone can trust to know the status of a certificate. And finally, by using the blockchain, we are effectively recording all the actions that are done by certificate authorities. So we can have much more transparency and accountability in their actions. And therefore, we can enhance the trust we have in these certificate authorities. So here are some other examples that of protocols that can be enhanced using blockchain. So I'm going to quickly go over this. The first one is DNS. I think this was mentioned this morning. So blockchain has proven to provide faster name resolution and synchronization. And it can also be used to mitigate attacks such as DNS cache poisoning attacks and DOS attacks. Now, blockchain can also be used to record TLS sessions to provide non-repudiation for content delivered by websites. And so this can be used as archiving service or even to build oracles from which we can get trustful information. And then finally, a major industry that can benefit from blockchain is the IoT industry. So with that, we can have secure and authenticated data exchange. We can automate the interaction between devices using smart contracts. We can use also the blockchain to timestamp events that are produced by IoT devices. And finally, we can have value exchange between devices using the blockchain native tokens. And this can bring lots of new use cases. So with that, I hope I gave you a good overview on how blockchain can be used to enhance the security of the protocols underpinning the internet. So now what I would like to share with you is so a new piece of research that I've been working on in the last couple of months. And that led to this technique called BCA, for Bitcoin Certified Addresses. So BCA is a new technique for auto-configuring IPv6 addresses that are bound to host public key. And the binding is secure by using the proof of work computed by Bitcoin. Now, I have to mention that this technique is actually derived from a standardized technique known as CGA, for cryptographically generated addresses. And so as Dr. Satya was mentioning this morning, this can be compared to like the blockchain version of CGA. So in order to understand what BCA does and what are its advantages compared to existing technique, let me quickly go over what address auto-configuration is and what CGA is. So IPv6 introduced this very nice technology, which is SLAC, for stateless address auto-configuration, which enables hosts to join a network and generate their own IPv6 address. And by shifting the work on the host, we are reducing costs of generating and managing these IPv6 addresses. So this can be very beneficial. Now, the addresses, they're generated by combining the subnet prefix with an interface identifier that is generated by host. And there are many ways this identifier can be generated depending on the SLAC mode that is used. And what we'll be looking at is the CGA mode. So with CGA, hosts generate their identifier simply by hashing their public key so that they can then sign messages using this public key, and everyone else can verify that the message was indeed sent by the claimed IPv6 address. So we are effectively preventing the spoofing of IPv6 address using CGA. Now, what I've showed you here is just plain CGA. So if we analyze the cost it would take for an attacker to find a different public key that binds to the same address, meaning the cost of spoofing the address, well, this cost is actually not very high, and it's relatively easy for an attacker to spoof an address. Now, hopefully, this is something that the CGA authors have thought of. And actually, in the CGA generation, in order to mitigate this attack, hosts have to solve something which is not called proof of work in the original paper, but this is actually a proof of work when you look at it. So address generation is done by finding this modifier value, such that when you hash the modifier together with the public key, the resulting hash starts with a certain number of zeros. So this is a proof of work as you have in Bitcoin, for those of you who are familiar. And so the effect of this proof of work is that it will increase the cost for an attacker to spoof an address. But at the same time, it also increases the cost for hosts to generate their address. And in practice, the proof of work that can be solved is a very limited one. And in effect, the security of CGA is relatively limited. So CGA addresses, in practice, they can only be used as short-term addresses, as temporary addresses that are typically used to bootstrap devices on local networks. Now, just want to make the parallel here with Bitcoin. So with Bitcoin, we also have a similar proof of work where nodes in the network, in order to append a block to the chain, they have to find this nonce value such that the hash of the block header starts with a certain number of zeros. The difference is that in Bitcoin, if you want to be able to solve that proof of work, you will typically require thousands and thousands of ASIC machines. And the reason is that the difficulty of this proof of work is extremely high. So comparing the two, with CGA, hosts, in order to solve the proof of work, will require on average a couple of thousands of hash trials, whereas in Bitcoin, it will require billions on billions of hash trials to find the correct proof of work. So now our idea with Bitcoin certified addresses is to reuse the proof of work computed by Bitcoin miners to enable hosts to generate highly secure IPv6 addresses. And on top of that, because hosts don't need to solve any proof of work at all, address generation is very efficient. So if we analyze the cost of a spoofing attack, then our calculation showed that it would require more than 100 million ASIC machines to be able to spoof an address, which would require a lot of money. So I'm gonna now quickly go over how BCA works, just to give you a brief overview. So hosts, in order to generate BCA, first have to register their public key on the blockchain. So they will broadcast a transaction containing a hash of their public key and a set of modifier values. And these modifiers will be used to generate multiple addresses bound to this public key. Now, address generation is as simple as doing one hash computation. So they will hash this modifier, the transaction and the block header, which contains the proof of work solution, and they will obtain their IPv6 address. Now, verifying the address is also very efficient. So for a verifier, it only requires 30 hash function evaluations, and all of the steps can be done offline. So to sum it up, and this will be my last slide. So BCA is a new technique derived from CGA that in the same way as CGA provides auto-configuration of IPv6 addresses with proof of address ownership, which has the benefit I've highlighted already. Now, compared to CGA, BCA provides a much stronger security guaranteed by Bitcoin miners, and therefore can be used as much longer-term addresses, whereas with CGA, you could only use them as short-term addresses. And so BCA addresses can be used to communicate peer-to-peer over the internet. So hosts can manage their address on-chain for instance, by updating these addresses, by revoking them, or in order to reach a peer, they can look on-chain what their IPv6 address would be. Now, it also provides a fast address generation, which is very beneficial for hosts with limited computational power, such as IoT devices. And it provides improved privacy because it is very easy to renew your IPv6 address. And finally, one of the, I think, major interesting aspects of BCA is that for the first time, we've shown that the proof of work computed by Bitcoin miners can be reused for other purposes than blockchain related, showing that the hashing part that is done by miners has a real intrinsic value. So we see with BCA proof of work as a shared resource, one that has public utility, which is not something that was previously envisioned. So thank you very much for your attention. And if you want to discuss this protocol further, or if you have ideas on how to develop it, I would be happy to have a chat with you. So here are my contact details and a link to our website.
Thank you so much. Close briefing. And you can still very interesting. Ask you now. Without further delay, I'd like to welcome for a very life-relevant topic, Dr. Mariam Ayash from IEEEEMBCS. The stage is yours.
Thank you so much.
Let's give her a big applause, please.
Thank you so much, Professor. So we will wait for the presentation and
Sorry, please.
Thank you. Okay, so, hello, everybody, and welcome to this speech, the session. Welcome to the second blockchain summit. I know it's the afternoon, and it's very hard actually to follow lectures. That's why I prepared for you something live, very light. I'm Professor Mariam Ayash, assistant professor here at EMTIC, and I started to work on blockchain since 2018, but I have experience from lots of I have experienced I had an experience in the distributed systems and peer-to-peer systems, and also I have an experience with healthcare domain. So that's why you are going to listen today to a talk about how blockchain and artificial